In probability theory, a conditional probability measures the probability of an event given that another event has occurred. If the events are A and B respectively, this is said to be the probability of A given B. It is commonly denoted by P, AB, or sometimes PB, A. In case that both A and B are categorical variables, conditional probability table is typically used to represent the conditional probability. The concept of conditional probability is one of the most fundamental and one of the most important concepts in probability theory. But conditional probabilities can be quite slippery and require careful interpretation. In statistical inference, the conditional probability is an update of the probability of an event based on new information. Incorporating the new information can be done as follows. We start with a probability measure on a sample space, say. Let the event of interest be A. If we wish to measure the probability of the event A knowing that event B has or will have occurred, we need to examine event A as it is restricted to event B. Since both A and B are events in the same sample space, are restricted to B is AB. Whenever P, B, 0 with the original probability measure on the original sample space, B must be the sure event in the restricted space and thus PB, B, must be 1. To derive P, AB, equals PB, A, so that P, BB, equals 1 we rescale P, AB, by dividing by P, B. This results in P, AB, equals P, AB, slash P, B, whenever P, B, 0 and 0 otherwise. Note: this approach results in a probability measure that is consistent with the original probability measure and satisfies all the Kolmogorov axioms. Note: the phraseology evidence, or information is generally used in the Bayesian interpretation of probability. The conditioning event is interpreted as evidence for the conditioned event. That is, P, A, is the probability of A before accounting for evidence E, and P, AE, is the probability of A after having accounted for evidence E or after having updated P, A. This is consistent with the frequentist interpretation. Note: P, AB, may or may not be equal to P, A. If P, AB, equals P, A and B are said to be independent. Definition: conditioning on an event, Kolmogorov definition, given to events A and B from the sigma field of a probability space with P, B, A0, the conditional probability of A given B is defined as the quotient of the probability of the joint of events A and B, and the probability of B. This may be visualized as restricting the sample space to B. The logic behind this equation is that if the outcomes are restricted to B, this set serves as the new sample space. Note that this is a definition but not a theoretical result. We just denote the quantity P, AB, slash P, B, as P, AB, and call it the conditional probability of A given B. As an axiom of probability, some authors, such as De Finetti, prefer to introduce conditional probability as an axiom of probability. Although mathematically equivalent, this may be preferred philosophically. Under major probability interpretations such as the subjective theory, conditional probability is considered a primitive entity. Further, this multiplication axiom introduces a symmetry with the summation axiom for mutually exclusive events. Definition with I-Florin algebra: if P, B, A equals A0, then the simple definition of P, AB, is undefined. However, it is possible to define a conditional probability with respect to I-Florin algebra of such events. For example, if X and Y are non-degenerate and jointly continuous random variables with density A, Y, X, AY, then, if B has positive measure. The case where B has zero measure can only be dealt with directly in the case that BI equals AYO, representing a single point, in which case, if A has measure 0 then the conditional probability is 0. An indication of why the more general case of zero measure cannot be dealt with in a similar way can be seen by noting that the limit, as all I approach 0, of depends on their relationship as they approach 0. See conditional expectation for more information. Conditioning on a random variable. Conditioning on an event may be generalized to conditioning on a random variable. Let x be a random variable taking some value from xn. Let A be an event. The conditional probability of A given x is defined as the random variable. More formally, the conditional probability p, ax, is a function of x. For example, if the function g is defined as, then. Note that p, ax, and x are now both random variables. From the law of total probability, the expected value of p, ax, is equal to the unconditional probability of A. Example, suppose that somebody secretly rolls two fair six-sided dice, and we must predict the outcome. Let A be the value rolled on die 1, let B be the value rolled on die 2, what is the probability that OR equals A2? Table 1 shows the sample space of 36 outcomes. Clearly, OR equals A2 in exactly 6 of the 36 outcomes, thus P, A equals 2, A equals A6 of 36 and equals A1 of 6. Suppose it is revealed that A plus bar permel 5, what is the probability A plus bar permel 5A? Table 2 shows that A plus bar permel 5 for exactly 10 of the same 36 outcomes, thus P, A plus bar permel 5, A equals A10 of 36. What is the probability that OR equals A2 given that A plus bar permel 5A? Table 3 shows that for 3 of these 10 outcomes, OR equals A2, thus, the conditional probability P, A equals 2A and A plus bar permel 5, A equals A3 of 10 and equals A0.3. Statistical independence. Events A and B are defined to be statistically independent if, that is, the occurrence of A does not affect the probability of B, and vice versa. Although the derived forms may seem more intuitive, they are not the preferred definition as the conditional probabilities may be undefined if P, A, or P, B, are 0, and the preferred definition is symmetrical in A and B. Common fallacies. These fallacies should not be confused with Robert K. Shope's 1978 conditional fallacy, which deals with counterfactual examples that beg the question. Assuming conditional probability is of similar size to its inverse. In general, it cannot be assumed that P, A B, A permel or P, B A. This can be an insidious error, even for those who are highly conversant with statistics. The relationship between P, A B, and P, B A, is given by Bayes' theorem. That is, P, A B, A permel or P, B A, only if P, B, / P, A permel A1, or equivalently, P, A permel or P, B. Alternatively, noting that AA copyright B equals BA copyrighter, and applying conditional probability. Rearranging gives the result. Assuming marginal and conditional probabilities are of similar size, in general, it cannot be assumed that P, A permel or P, A B. These probabilities are linked through the formula for total probability, here. This fallacy may arise through selection bias. For example, in the context of a medical claim, let SC be the event that a secular S occurs as a consequence of circumstance C. Let H be the event that an individual seeks medical help. Suppose that in most cases, C does not cause S, so P, SC, is low. Suppose also that medical attention is only sought if S has occurred due to C. From experience of patients, a doctor may therefore erroneously conclude that P, SC, is high. The actual probability observed by the doctor is P, SCH. Over or underweighting priors, not taking prior probability into account partially or completely is called base rate neglect. The reverse, insufficient adjustment from the prior probability is conservatism. Formal derivation. Formally, P, A B, is defined as the probability of A according to a new probability function on the sample space, such that outcomes not in B have probability 0 and that it is consistent with all original probability measures. Let I copyright be a sample space with elementary events I permel. Suppose we are told the event bar AI copyright has occurred. A new probability distribution is to be assigned on I permel to reflect this. For events in B, it is reasonable to assume that the relative magnitudes of the probabilities will be preserved. For some constant scale factor I plus or minus, the new distribution will therefore satisfy. substituting 1 and 2 into 3 to select I plus or minus. So the new probability distribution is. Now for a general event A. See also, Ball-Kolmogorov paradox, chain rule, class membership probabilities, conditional probability distribution, conditioning, joint probability distribution, Monty Hall problem, posterior probability, references. External links, Weierstein, Eric W., Conditional Probability, Math World. F. Thomas Bross der Wyatt ihr Perfekt oder die Beta Paragraph Rendmacht kleiner Wahrscheinlichkeiten, Spektrum der Wissenschaft, Vol. 2, 110 113. Conditional Probability Problems with Solutions, Visual Explanation of Conditional Probability.